And we are starting our next session with Maria, who is dialing in from the west coast of US. So Maria Dimakopoulou is a senior machine learning engineering manager in the home personalization team at Spotify. And so her team the focus of her team is combining cutting-edge advances in machine learning, causal inference, and reinforcement learning with scalable engineering to run Spotify home recommendations. And before that, Maria was at Netflix, and before that at Google. And I just realized that's a conversation we didn't have yet since we were both at Google. At a later time during the mingle, perhaps. Please, Maria, we're looking forward to your talk.
Okay, thank you so much, Galina, for the introduction. And hi, everyone. I'm joining you from California, as Galina mentioned. So you see it's still the night over here, but maybe we will see the glimpse of sun when the presentation ends. So yes, my team's focus on Spotify is on ranking and construction of Spotify's homepage. And today I'm going to present to you two important considerations for using adaptive learning effectively for decision-making in practice, and particularly for personalization. The first consideration is that of model estimation with adaptively collected data, and the second consideration is that of exploration in adaptive learning algorithms. And as we will see, both considerations are very central for our personalization models, and particularly the homepage personalization models at Spotify. So let's jump right in. First, what is adaptive learning? In adaptive learning, we will have an agent, such as Spotify's recommender, and also a user. And this agent is going to interact repeatedly with the world, like the user, and learn from these interactions. The agent is going to observe a state S, such as the user's listening history. Then it's going to take an action A, such as a personalized homepage in our example. And finally, the agent will observe a reward R, which depends on both the state of the user and the action the agent took. And this reward can represent how much the user engages with the recommendation of the Spotify home recommender. Optimizing the user experience via personalized recommendations can be seen as an adaptive learning problem. And to make successful recommendations, Spotify needs first to generalize from the data it has, second, explore in order to get data to learn from, and third, plan for the long-term user satisfaction. In fact, there isn't one Spotify service. There are hundreds of millions of Spotify services unique for each one of the Spotify users. And more formally, in adaptive learning, we can define a value function Q. And this value function Q represents the value of taking action A from state S. And this value function can represent either an immediate value or a long-term value. And when it represents an immediate value, such as how much a user streamed in one Spotify session, then this adaptive learning problem is called the contextual bandit. And the value function Q is estimated from individual state action reward observations. When the value function represents a long-term value, such as how much a user streamed in all the Spotify sessions of a month, then this adaptive learning problem is called reinforcement learning. And the value function Q is estimated from entire state action reward trajectories. So after estimating the value function Q, the agent is going to need to balance exploration with exploitation. And this means that the agent will need to take actions first that bring the maximum value according to the estimated Q function, but also take actions in order to collect learning data for state action pairs that we do not know yet how to estimate this Q function accurately. And some of these algorithms that balance exploration with exploitation are first epsilon greedy, take the action that maximizes the estimated Q function with probability 1 minus epsilon, and then with probability epsilon, take a random action in order to learn. Then we have the upper confidence bound approach, UCB, which forms the upper confidence interval for the Q value of each action A from state S, and then takes the action maximizing these upper confidence intervals. And third, we have an approach called posterior sampling or Thompson sampling, which forms a distribution over the value function Q draws a sample from that distribution, and then takes the action maximizing the drawn samples. So as we see, estimating the Q-value function accurately lies at the heart of an adaptive learning agent. And then, after we do this estimation, this estimated Q function is paired with various exploration strategies. And let's focus on the contextual bandit setting, that of the immediate reward. Traditional model estimation entails concatenating the action information with the state information as input to a model, and then trying to predict the immediate reward R. And the loss function for a continuous reward looks like this mean squared error over here, targeting predictive accuracy of the fitted model. However, adaptive learning doesn't really ask a prediction question. It really asks a causal question, and prediction is just a proxy to answer that. Adaptive learning really asks, what will happen if I take this action from my present state versus another one? There is an inherent counterfactual. That's why we say it's a causal question. And this is why the value function estimation needs to target consistent causal effect estimation rather than goodness of fit or predictive accuracy of the model measured by the mean squared error. If the model targets mean squared error versus causal effect estimation, decision-making may fail. And it may fail due to various reasons. It may fail due to unintentional regularization of the action signal when the model exhausts its capacity to more predictive state signals. One would say, isn't the entire user listening history more predictive about what the user is going to listen to next than a single Spotify recommendation? So maybe that single action is going to be washed out by the stronger signal of a longer listening history. This is what we mean when we say unintentional regularization of the action signal. And also decision-making may fail due to selection bias in the data. The agent progressively creates unbalanced training datasets because in each region of the state space, it takes actions that are predicted to perform well with higher probability than actions that are predicted to perform worse. This is natural. This is what the adaptive learning needs to do, learn to take better actions depending on the user state. But this type of unbalanced dataset is going to later cause problems, bias problems, in our estimation of the value function. And these types of biases, regularization bias, selection bias, are both aggravated in the presence of covariate shift and in the presence of mismatch between the underlying model of the agent and the true data generative process. And both these issues, both model misspecification and covariate shift, are common in practice. Model misspecification, because we do not know the true reward model underlying the responses of the user. And also, we see covariate shift happening all the time, meaning that the distribution, the state distribution of the users changes. For example, when early adopters interact with the service more in the beginning, and then their interactions affect the policy that the service takes for all the users, but having trained on early adopter data. So the focus of our AAAI 2019 paper with Zhengyuan Zhu, Susan Nathan, Guido Imbens from Stanford was to address these challenges in the online contextual bandit setting. We propose replacing the regular model training that lies at the heart of every contextual bandit agent with important sampling weighted training. And the agent takes an action A from state S with some probability P. This probability P is called the propensity score. For stochastic agents such as epsilon greedy and Thompson sampling, this propensity score is known at each step. And for deterministic ones, it can be estimated from state action data. Then, for estimating the parameters of the Q function, instead of running the unweighted regression, the loss function we saw earlier, we can run an important sampling weighted regression where each data point in the loss function is weighted by the inverse propensity score 1 over pt, as we see here. And since the propensity score of an observation really represents the probability of taking action A from state S, what important sampling weighted training does is that it upweighs state action observations that are rare and makes, as a result, the action selection as good as random, even though in practice it's imbalanced because it outweighs the threat observations. And this is why the term importance sampling weighted regression is often referred to as balancing. And these bandits that use importance sampling weighted training are also referred to as balanced bandits. And then in our NeurIPS 2021 paper with Aurélien Bibot, Nathan Kalous, Antoine Chambaz, and Mark Vanderlaan from Netflix, Cornell, Berkeley, and University of Paris, respectively, we provided for the importance sampling weighted regression first of their kind theoretical guarantees when this importance sampling weighted regression is applied on data collected by an adaptive learning agent. And we also demonstrated in an exhaustive empirical study that importance sampling weighted regression clearly outperforms unweighted regression, the loss function we saw earlier, and other weighting schemes, particularly when we have model misspecification. So let's build a bit of intuition around why this is happening. Over here, we have a simulated example showing why we should expect better performance from importance sampling weighted bandits, which we call balanced bandits, as I mentioned. So suppose that the user state is represented by a two-dimensional embedding, and these are the reward surfaces of 3 podcast recommendations over the entire user space. Now, if we zoom in to the early adopter part of the state embedding space, the reward surfaces look mostly flat because they are around these optimal points over here, this local extrema. And since we get the initial training observations from the local extrema part of the space, of the user space, this is going to represent the early adopters. But when we transition to giving recommendations to the entire user base, we will have covariate shift. So even though the red podcast is the best action for most users, the regular bandits, which have trained on the early adopter datasets, like these figures here on the right, are going to have trouble learning that the red podcast is in fact the optimal action. So we now see that covariate shift combined with model misspecification, meaning with an agent that has linear terms in its reward model than having these quadratic terms that accurately represent the quadratic reward surfaces. Both covariate shift, due to the early adopters that come first, and model misspecification are going to lead to estimation bias that results into an incorrect decision making. And this incorrect decision making is going to happen for both types of Thompson sampling and UCB, so both types of exploration based on uncertainty, when Thompson sampling and UCB train with a regular unweighted regression. So they will both land on the yellow podcast when they should be recommending the red one. And this is the first row, Thompson sampling, UCB with unbalanced weighted regression. By using balancing, however, rare actions across the state region are weighted much more than frequent ones. And balanced regression with stochastic exploration, that stochastic exploration of Thompson sampling, is going to escape this bias much faster. And here we see that balanced Thompson sampling identifies the correct recommendation almost from the beginning, that it should be recommending the red podcast. However, the deterministic exploration of UCB makes dealing with both covariate shift and model misspecification quite challenging, even with balanced regression. And that shows us that it's both the correct estimation techniques and the correct exploration techniques that matter together for practical decision making. And this results from the simulated example hold up in a large-scale empirical study we ran on a benchmark of 300 classification datasets, which can be turned into a bandit by only revealing the reward of the chosen action or class instead of all of them. And in this figure here, each point represents one of the 300 datasets, and with blue we show when the balanced Thompson sampling agent has higher reward compared to regular Thompson sampling and UCB with unweighted regression, compared to balanced UCB, and compared to a model-free baseline bandit that doesn't use any model, it uses policies, called ILTCB. And we see that balanced Thompson sampling outperforms all other 4 baselines, showing that both the right estimation and the right exploration matters. And we need to use balanced regression paired with Thompson sampling exploration for practical online learning. So far we have established the strong practical benefits of importance sampling weighted regression for adaptive learning. But we can do even better. We incorporated importance sampling weighting in order to correct for the bias in adaptively collected data. But when the propensity scores become small, and this can be expected in adaptive learning as the agent starts sampling suboptimal actions less and less over its learning horizon. So when the propensities become small, this may lead to high variance because this importance sampling this propensity score appears in the denominator. When it becomes small, it can really explode the variance of these estimators. And this is common both for the inverse propensity weighted estimator we saw so far, this is represented on the left, and also for an augmented version of inverse propensity weighting called doubly robust. It's called augmented because it fits an outcome model and then applies a propensity correction, not directly on the reward as we see on the left, but only on the estimation error of the fitted model. So this augmented version of IPW called Doubly Robust also has propensity scores, but we should expect its variance to be a bit lower from inverse propensity weighting. However, both IPW and Doubly Robust are going to suffer from large variance with small propensities, albeit Doubly Robust's variance is going to be a little bit lower. But another issue is due to the importance sampling weights becoming large, is that both IPW and Doubly Robust will not be asymptotically normal. And asymptotic normality is a desirable property when we rely on normal confidence intervals for post-learning inference, and when during learning we use exploration strategies such as UCB and Thompson sampling, which often use normality assumptions. And we clearly see in these pictures that the distribution of IPW and Doubly Robust are not looking normal. And one way to address this lack of asymptotic normality and the exploding variance is to attempt to stabilize the variance of the doubly robust estimator by replacing the equal 1 over capital T weighting across observations, T is the number of observations we have, with an adaptive weight that differs across observations. So instead of having this uniform weighting and averaging across observations, we are going to apply different weights across observations that are going to downweigh some of these observations. And these weights, sigma hat T inverse, are called adaptive because they rely on the history of past observations up to time T minus 1. And they aim to undo the exploding variance of the importance sampling weights as the propensity scores become small. And this family of estimators is called adaptive doubly robust. In their paper, Vitor Haddad, David Hirschberg, Rohan Zhan, and Susan Nathan from Stanford in 2019 first proved unbiasedness and asymptotic normality for unpersonalized adaptive learning agents using these adaptive doubly robust estimators, when they chose the weight of each observation T to be square root propensity score of observation T. But this result doesn't carry over to the personalized policy setting where many of the practical applications lie. So our focus in our second NeurIPS 21 paper, post-contextual bandit inference with the same co-authors as before, proposed the contextual adaptive doubly robust estimator for environments and policies where the reward generation and action selection is based on some state information and is therefore personalized. The estimator looks very similar as before. In fact, it's the same as before, but now with state information, ST, everywhere. What is challenging in that setting is how to choose this adaptive weights sigma hat inverse. And this term DT over here is called the efficient score of an observation. And in fact, sigma hat square needs to be an estimate of the variance DT in order to be used as an adaptive weight. The variance of term T can be decomposed into the expectation of DT square minus square of expectation DT. But the problem is that we only have one draw under the distribution that collected observation T, the policy that collected observation T, to estimate these expectations. We overcome this challenge by casting the doubly robust score of each one of the previous observations before time t as if it was drawn from the policy that we landed at time t. And this is represented by this how d tau. And then we estimate the expectations by taking averages of this had d tau square and had d tau weighted by the important sampling weights pt, which is a propensity score of observation t, divided by p tau, which is the propensity score of a previous observation tau. And using as weights the 1 over sigma hat t, we will get the contextual adaptive doubly robust estimator, which is both unbiased and asymptotically normal, both for unpersonalized and personalized policies. In fact, this was the first unbiased and asymptotically normal estimator for data collected by a contextual adaptive learning agent. And here we compare our contextual adaptive doubly robust estimator against many other estimators in the literature in terms of robustness of the confidence intervals on more than 50 public classification datasets. And again, we converted the classification dataset into a contextual bandit logged by a random forest bandit, and then evaluated how often the true value of 3 new, completely different policies, which is each one is shown in each one of these 3 rows over here, fall within the 95% confidence interval of the estimator. So how often the 95% confidence interval of our estimator covers the ground truth of these new policies. And this is called coverage. Each dot again represents a dataset, and it is blue when the contextual adaptive doubly robust estimator has significantly better coverage than other baselines. And we see that across all our experiments, we observe that the confidence interval of contextual adaptive doubly robust has better coverage of the ground truth than any other baseline, which can be attributed to both the unbiasedness but also the asymptotic normality of contextual adaptive doubly robust for agents and environments that are personalized. So the last question we ask before we close in this estimation topic is that can we pair this unbiased and asymptotically normal adaptive doubly robust estimator with an online learning algorithm and achieve better performance online in our personalizations in practice? And the answer is yes. So in this recent paper co-authored with Jimei Ren and Zhengyuan Zhu from University of Chicago and NYU Stern, we proposed doubly adaptive Thompson sampling, which uses the distribution of the adaptive doubly robust estimator we saw earlier in place of a posterior in a Thompson sampling algorithm. So instead of using the Bayesian posterior updating rules of Thompson sampling, we will take as the posterior mean of an action the adaptive doubly robust estimator that we saw earlier, and as a posterior variance, the variance of that estimator, which is also estimated in closed form. And as we just saw, this estimator has been constructed to have a normal distribution. Therefore, we can use this normal distribution as the posterior of the action. And the decision making is just as before, using samples from all the action's posterior distributions and selecting the action with the highest sample. And finally, to bound the propensity scores, doubly adaptive Thompson sampling eliminates arms if their probability of being better is less than 1 over learning horizon. But we also evaluate a simpler variant of doubly adaptive Thompson sampling that instead of arm elimination uses propensity score clipping, meaning replaces the propensity score of an observation with the max of a clipping threshold and that propensity score, so that it doesn't go below that clipping threshold. And the motivation of using adaptive doubly robust in online learning is that the adaptive doubly robust estimator corrects the bias due to adaptive data collection, and also that the adaptive doubly robust is asymptotically normal, thus pairing well with Thompson sampling exploration scheme. And as a result, doubly adaptive Thompson sampling outperforms both traditional Thompson sampling and UCB, as well as the Thompson sampling with importance sampling we saw earlier. All that while doubly adaptive Thompson sampling matching the finite time regret bound guarantee. And indeed, we see that in the simulation, we compare doubly adaptive Thompson sampling and doubly adaptive Thompson sampling clipping with traditional Thompson sampling and UCB in 20 simulated domains with number of functions ranging from 5 to 50 and 2 noise settings, a high noise setting and a low one. And we see that doubly adaptive Thompson sampling and doubly adaptive Thompson sampling clipping, the blue and green one over here, achieve smaller regret, meaning the reward that the algorithm forfeits by choosing an action other than the optimal one is lower, so lower is better. And the regret is lower in both noise settings and also for small and large action spaces. Also, we see that the doubly adaptive Thompson sampling agents have smaller stopping power, meaning they can identify the optimal action much faster. And these results carry over in an online A/B test that was run at Netflix, where again, doubly adaptive Thompson sampling was compared in terms of regret and stopping power across baselines. And we see again that the blue and green algorithms over here bring significant improvements in terms of both cumulative regret and in terms of performance. So the parting thoughts of this topic is that estimation lies at the heart of any adaptive learning agent. And if we want to have reliable decision-making in practical problems based on adaptive learning agents, we have to get estimation right. And we saw that estimation online during adaptive learning and offline post-adaptive learning can be very challenging. And these challenges only compound as we move from immediate rewards and contextual bandits to long-term value and reinforcement learning. The key idea we covered in this talk is that incorporating sophisticated causal inference estimators into online learning agents and pairing them with efficient exploration strategies such as Thompson sampling significantly improves the performance of the adaptive learning agents in practice, and this improvement often comes with state-of-the-art theoretical guarantees. I'd like to thank you for your attention and feel free to reach out with any questions.
Thank you very much, Maria. Very interesting. This talk is definitely more targeted towards the research part of our audience, which is non-trivially large actually over here. We only have a few minutes, so I have two questions sort of from the audience, and then we'll see if we will have time for one more thing. So one question that I typed in actually from somebody: given prior experience of users, do you need to do any pre-processing or sample grouping before Thompson sampling?
Yeah, that's a great question. So it's very helpful, actually, even if you haven't started putting in practice a continuous retraining algorithm, an adaptive learning algorithm like Thompson sampling, to collect any prior observations you have from the users with any logging policy in order to put in Thompson sampling informative priors. So instead of starting with an informative priors, say reward 0 and a very large variance, which basically says, I have no idea what the reward my action is going to do, actually use this previous samples as a pre-processing step in order to set up an informative prior.
Okay, thank you. And the other question I also have from the audience is, how long does it take to train a good model?
So it depends. This question has multiple interpretations. First is kind of how long does it take to find a good model, which is iterative in terms of, like the contextual bandit work has been going on since 2010 with that first paper from MSR on contextual recommendations, and we're still getting better and better models online. So it can take years in terms of the research and the improvements. In terms of the actual training, it really depends on the model architecture one is going to use. And if someone wants like very fast iterations, linear models do get a first order effect and can be very fast in production, whereas like neural networks, of course, depending on the amount of features we have, can take a little bit more. Generally, we want to be able to retrain our models in matter of days so that we capture new information. So we want to have very frequent retrainings, ideally daily.
Yeah, makes sense. I had one brief question, but I think we'll skip it because we're running out of time. Thank you very much, Maria. Really appreciate it, and hope you enjoy your day in California as we roll into the evening.
Thank you for the invitation, and thank you for putting together this excellent event.
Thank you.